Hello, welcome back to another video tutorial on Chapter 10 for BC Calculus. This time, it feels like we've been playing with Taylor's Theorem for a while, but that's the official title of this section, Taylor's Theorem. In this section we have a few things that we want to look at. We're going to look at truncation error with a calculator, truncation error for geometric series, and then finally truncation error for alternating series. One of my favorite parts of the BC Calculus curriculum is the first time I start building a Taylor series for sine of x in Desmos. I just love writing it as a sigma notation with n as the top limit and putting a slider on and showing how it just glues itself to sine of x for all x, sort of going from the center out in both directions. But in spite of that, in spite of how cool that is, very often we're not actually adding up an infinite number of terms. I mean, who could? So we want to use what's called a Taylor polynomial, just part of the infinite series, a truncated piece of it, to approximate the sine function. But how many terms should we use, and how good's the approximation? So example 1 says, find a Taylor polynomial that will serve as an adequate substitution for sine of x on the interval negative pi to pi. Well, the first thing, it's a bit of a stumper, is what do they mean by adequate? And so one reasonable suggestion is that we want the Taylor polynomial to be within 1/10,000th of sine of x on the interval negative pi to pi. Now, we can cheat a little bit and don't have to worry about the whole interval, because one of the things that we have learned about power series is they approximate the function they represent most accurately at their center, where they're always correct, and as you move out on the interval of convergence, they are less and less accurate. So we really just need to worry about how close sine of x is to the Taylor polynomial we create at negative pi and at pi. So I created a Desmos share for this, and I will put the link on Moodle, and that will allow you to use a slider to find the answer. For the Taylor polynomial, I'm using the following. When you expand this out, of course, you get the familiar x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And we stop at the top, n, which I will let be a slider. I've written a couple of expressions, and I want to see when they first drop below 0.0001. Here are the expressions. So for any value of n, p of x will be the Taylor polynomial with n terms. And we want to find the difference between p of x and sine of x at each of pi and negative pi. So I use these two expressions. One thing that shouldn't be surprising at all is, since both sine of x and p of x are always going to be odd expressions, d1 and d2 are always going to be equal for any particular value of x. And so I used the slider, and I found out that when I got to n equals 7, the conditions were met. Here's a quick screen grab from Desmos. This is the Desmos share. You can look at it if you want. You can play around with the slider yourself, but notice if n is 7, d1 and d2 are both 0.00002, which is definitely less than 0.00001. On the other hand, if I set n back to 6, it's too large. So this is the solution to this question. Without going too much into detail, the moral of this story here is that we can make p of x, a Taylor polynomial for sine of x, get as close as we want to sine of x for any value of x, simply by including enough terms of the Taylor series in our polynomial. It'll never be exact except at the center, but we can make it arbitrarily close. So if we really want it to be exactly equal to sine of x, we have to use an infinite series. But whenever we use a polynomial, we always get truncation error. Truncation error is the error that we get because we left off an infinite number of terms in the tail of the series to truncate an infinite series down to a polynomial with a finite number of terms. Sometimes it's very easy to calculate truncation error exactly. Example 2 asks us to find a formula for the truncation error if we use 1 plus x squared plus x to the fourth plus x to the sixth to approximate the function 1 over 1 minus x squared. Well, the first thing I want you to point out or to notice is that they've said specifically on the interval -1 to 1. I want you to remember that this example is one of those of the form a over 1 minus r, which was a plus ar plus ar squared plus dot dot dot. And it was only valid when the absolute value of r is less than 1. And that's why in this case that power series will only converge to 1 over 1 minus x squared between -1 and 1. But think about what the rest of the series is. So we have 1 over 1 minus x squared, and it's equal to 1 plus x squared plus x to the fourth plus x to the sixth plus x to the eighth, x to the 10th, in general x to the 2n minus 2 forever. But we're going to cut it off, and we're only going to keep the part up to x to the sixth. Well, it's easy to estimate the value of the remaining piece because the remaining piece is itself a geometric series. And the value of the tail is, again, a, in this case, x to the eighth, over 1 minus r, or over 1 minus x squared. So this represents the error term. If I use just up to the sixth to represent the value of 1 over 1 minus x squared, the remaining piece is always within the interval of convergence exactly equal to x to the eighth over 1 minus x squared. So for instance, if I used 1 over 1 minus x squared, I wanted to evaluate it with 1 plus x squared plus x to the fourth plus x to the sixth at point 1, let's do a little calculating. At point 1, the value of 1 over 1 minus x squared is 1 over 0.99, or 1.010101 forever. How about the next piece? At 0.1, 1 plus x squared plus x to the fourth plus x to the sixth, which is the sixth degree polynomial we're using to approximate 1 over 1 minus x squared, that turns out to be 1.00010001, and you'll notice the actual correct answer, 1 over 1 minus x squared, versus the other, they're off by a little bit. And the amount that they're off by is exactly x to the eighth over 1 minus x squared. So what is 0.1 to the eighth over 1 minus 0.1 squared? And if you calculate it, you'll find that the difference is exactly the difference between 1 over 1 minus x squared and 1 plus x squared plus x to the fourth plus x to the sixth at 0.1. So that's the lesson here. Sometimes we can't get, and in fact most of the time we can't get an exact answer for the truncation error. If we could, then we could just find the actual value, just take our approximation plus the exact truncation error and we'd find the exact value. But sometimes we just get sort of an approximation or sometimes an upper bound for it. Let's take a look at an example you've seen before. Not sure you remember this. This is very important in this part of calculus. This is called the alternating harmonic series. And we talked about earlier how it converges very, very slowly, but it converges to the natural log of 2. And there's a little theorem here that helps us understand why. We start off by moving or adding 1, and then we subtract a half. Now we add a third. Now we subtract a fourth. So it's like I step right 1 yard, left half yard, right third yard, left quarter yard. Each time I'm moving a smaller distance than I did the previous time and in the opposite direction. So it's pretty obvious that I'm going to be homing in on some particular final answer as I get further and further and further. Here's a diagram that might help a little better. The key theorem involved here is the alternating series error bound. If a series has the following three properties: 1, the terms alternate in sign; 2, the terms decrease in absolute value; and 3, the limit of the nth term is 0, then the truncation error after n terms will be less than the absolute value of the very first term you left off, the n plus 1th term. So let's suppose that I used, the following part to approximate the natural log of 2. Well, I typed this into my calculator, and the calculator said that this part so far, 1 minus a half plus a third minus a fourth plus a fifth, is 0.783 repeating. Now, just for comparison, the natural log of 2 is, these two differ by 0.090186. But the key thing is, what was the first term we left off? And the first term we left off was minus 1/6. And negative 1/6 is negative 0.166 repeating. And you'll notice that the difference between the approximation and the correct answer is less than the first term we left off. Not only is it less than, but the first term we left off was negative. That tells me that the natural log of 2 is actually lower than my answer so far, because the first term I left off is negative, so our exact answer is lower than our approximation. Anyway, that concludes the first part of 10.3a on truncation in power series. We took a look at it with a calculator and a Desmos example. We took a look at the truncation error in a truncating a geometric series, and finally we looked at the alternating series error bound, which is applies when you have a series that alternates and gets smaller with a limit of 0. And that's a very, very useful theorem. So until next time, stay healthy and stay well. And don't try to keep yourself amused too. Bye-bye.